Guys, I chose the subject tonight of AMD, pathology or aging physiology, and then mechanisms for early intervention. Sorry, could you go back?
I did.
Yeah, okay. And most people look at AMD. Unfortunately, a lot of patients come in late when they've got a neovascular problem. And most of the emphasis in recent years has been on the genetics of AMD. Next. Sorry about this. Next slide. Okay, well, I think everybody should remember that it was 1953 that the classical Watson and Crick paper appeared in Nature. And 50 years later, we had the entire human genome and the Book of Man. Now, when you look at AMD, currently we've got 54 candidate genes at 34 different loci. So if we're going to be dependent in future upon gene therapy and personalized medicine, this is going to be a long job with 34 different loci and different effects of the genes. Next. Gives you plenty of thinking time. I need a robotic changer. Okay, now the bit that tends to get ignored, but we all know, is the biggest risk factor in AMD is actually aging. So it would appear that what we actually see in the eye is a combination of, in many cases, a defective gene, but an underlying aging phenomena in the outer retina. Now, the retina is a very special case because we're dealing with aging plus stress, and the retina is the only part of the body where optical radiation penetrates inside the body. And not only does the optical radiation penetrate inside, but it has to be absorbed, and it's absorbed in both the photoreceptor cells and the retinal pigment epithelium. Next. Okay, well, everybody knows that photoreceptors develop this wonderful mechanism. The cells themselves can't divide, but they do remanufacture on a constant basis their light-sensitive discs containing a double membrane system with rhodopsin and, in the case of cones, other visual pigments. Now, this regenerative process in turn leads to problems during age. First of all, we see a build-up of lipofuscin in the retinal pigment epithelium, click. Then we see a build-up of waste products within Bruch's membrane, click. And unfortunately, in many individuals, this is sufficient that we see subretinal debris in the form of drusen, which displace the overlying pigment epithelium. So this process of clogging both the pigment epithelium and Bruch's membrane have serious consequences for visual function, in that all the transport properties through Bruch's membrane and the outer retina progressively decline with life. And we see an exponential decay of the ability of water to move out of the retina, but there is a linear decay of amino acid transport and carrier transplant port. So I had a very simple concept, and that was, as a function of aging, all cellular systems decline. They start very wonderful systems at 100%, and then as you get older, the function progressively declines. And if you're unlucky enough to have a defective gene, then the rate of decline may significantly increase. So I wondered if you could push up the basic aging curve and essentially rejuvenate the outer retina, you'd probably be dead before the combination of aging and a genetic defect led to significant visual loss. Now, this resulted in a huge number of papers from my group over the years. Next. So I'm not going to go into this in great detail, but there are getting on for 100 publications in which we've investigated this process, and it's clearly related to a progressive decline in the body's natural processes to degrade the deposits in Bruch's membrane and to clear the lipofuscin. Now, it turns out that on laser impacts, the pigment epithelium is caused to migrate and divide, and that releases MMPs in an active form, and they can clean the system up. So you can't use conventional laser because you destroy the photoreceptor cells, the very cells you're trying to preserve. And so we came up with a nanopulse laser, and most importantly, a discontinuous beam distribution. So the picture you see there, the dark areas are cells that have been raised above threshold, and the light areas are cells that have not been harmed in any way by the laser. So the good news about that is the dark cells result in production of metalloproteases to clean the system up, and the green cells sustain vision in the overlying photoreceptors. So if you hit a patient's eye with this, they have no perception that they have had a laser impact. Next slide. And again, a great deal of work went on to show that the impact actually caused changes which effectively rejuvenated transport in the outer retina. You can see there's an almost exponential increase in transport associated with MMP9. So this laser initially went to trial by our group at Moorfields with Peter Hamilton, and it was used initially to treat diabetic retinopathy because if it would improve transport, it should result in clearance of the subretinal fluid. And this was headed up by Lucia Pellicini and showed very clearly that this system was extremely effective in clearing macular edema in diabetics without any collateral retinal damage. Subsequently, next slide, the system was trialed for AMD, a multicenter trial by Robin Geimer in Australia, and the results were a little bit confusing until the retroanalysis showed why. Patients with classical drusen, i.e. beneath the retinal pigment epithelium, and that's what the laser was designed to cope with, showed a significant improvement and a significant delay in transfer between dry to wet AMD. By contrast, those individuals with pseudoreticular drusen, i.e. debris in front of the pigment epithelium, showed a worsening. So that was difficult, and some protagonists have said, oh, you shouldn't use it. My response immediately was, no, you should actually review patients going into these trials. So currently we're setting up a new trial under FDA guidance for a multicenter trial in the US, the SLAM trial, in which we will absolutely address the issues of where debris is. And I think Adnan showed very early on the beauty of modern imaging devices in giving us this ability to discriminate. So next, we have good cross-correlation with the production of MMPs and treating ocular conditions. Some of you will have followed the LIGHT trial. So the LIGHT trial for glaucoma, it took 20 years. I can remember our first experiments with SLT systems, which showed very significant changes, but the trial took 20 years to complete. Thank goodness it's here. now a recommendation that perhaps it's the first line of treatment for diabetics. 2RT trial, the lead trial, 12 years from initiation of the laser system. Same mechanism, upregulation of MMPs, in this case, cleaning collagen in Brooks membrane as opposed to collagen in trabecular meshwork. Hence, we are now really excited about the new SLAM trial with a more rigorously organized patient entrance requirements. Now, just think about this. Treatment for AMD, we're only treating between 7 and 10% with anti-VEGF treatments. Huge cost to the NHS, absolutely huge cost. So this laser would actually save an enormous amount of money if we can significantly reduce the conversion of dry to wet. And now we'd be dealing with 90% of the patients instead of less than 10%. Next slide. So finally, in response to Aline's questions, what problem does the chosen technology solve? Its sight-threatening consequences of AMD. How does the innovation solve the problem? It removes aging in Brooks membrane and rejuvenates transport processes. How does this innovation change the patients? Well, it reduces blinding consequences. How does this innovation change the life of the clinicians? Great. It puts the doctor back in control and reduces workload. Don't have to do all those horrible injections. Why does this innovation excite me? Well, it's an interesting combination of saving sight, saving clinical time, and saving money. Thank you. And thank you, Chris. Sorry about the delay.
This is really wonderful talk. Thank you so much. My question is, when it will be possible to use this technology, when we will able to see in the market or in our clinic earliest?
Well, the laser has undergone an ownership change. It was, I took my patents to a company called LX in Australia. LX has been sold to Quantel. But we retained the 2RT system, and now that's owned by Nova I R&D, which is a startup which is currently raising funds for the next trial. LX did sell a number of systems, and they've been used in many countries throughout Europe. Unfortunately, a lot of individuals didn't stick to protocols, but hopefully, clinical trial, if this time we have a better entrance input. The FDA has agreed some interesting outcome criteria, and we're looking at probably 3 years from commencement of trial, which should be first quarter next year.
Wow, okay, thank you. Do you have any question from our panelists?
John, really great talk, and hopefully as future trials, when you get rid of the reticular pseudodrusen, may show much more positive results. Just a sort of question that always comes up from the fellows and residents is they get confused. Micropulse versus your laser versus 670 nanometer rejuvenation.
Yeah.
Can you summarize that and what the pros and cons or the evidence base for
Okay,
those?
well, since the first use of lasers for retinal treatment in the late 60s, early 70s, those used millisecond pulses, which were actually designed to destroy ischemic retina. So the original design was to destroy all the layers of the neural retina. Then we thought, well, actually, if we could shift oxygen from the choroid to the retina by destroying the major oxygen consumer, the photoreceptors, that led to shorter pulses, and then the development of the microsecond pulses. But with microsecond lasers, you still have thermal spread into the photoreceptor cells, one, and because you destroy a plaque of cells or stimulate a plaque of cells, you switch off all the transport within the plaque. So cells will secondarily degenerate in that area. That's why we went to nanosecond with this discontinuous pulse duration. The later system, I'm not sure how that works. You know, I've been in the laser field for 50 years, and we had that discussion earlier about when you don't know what you're doing, do it neatly and say it with gravitas. So I don't know how that system works. I understand the others, and the reason why we've gone shorter and shorter and shorter is to limit collateral heat flow. And with the nanosecond pulse, there is no heat flow. It's all consolidated around the pigment granules. That discontinuous beam preserves photoreceptors. Who knows what tomorrow's innovation is, but I'm really excited about this one because it could save the NHS a lot of money and you a lot of time.
Maybe I'd like to ask you.
Is there any question?
Yes, it's an interesting concept. I think that you destroy or tickle a few cells and probably the others multiply and move in and produce maybe matrix metalloproteases that will sort of help with the extracellular matrix. But in general, in biology, if you do something like that, the effect is temporary. So is it just one treatment you're proposing or a series of treatments that have to be repeated at a certain interval?
It's a good question. It probably takes, well, it certainly takes 40 to 50 years to build up your debris. So it's a bit like hair in the plug hole of your shower. It builds up and you pull it out, whoosh, and everything goes back. So if it took 50 years to get there, you treat it and clean it up, it may take another 50 years to build up again. So that's the concept. It should be a one-off. And ideally, I'd like it to be prophylactic. I wish I could have had it when I was 40.
So then the other question is, you know, each person is different. So how do you titrate? It can't be sort of one size fits all.
Yeah, that's another issue. And what we've been working on most recently is titrating input number and dosage of MMP release. Now, ideally, the first sign here is changes, well, the first sign is changes in visual pigment concentration in the outer segments. The second sign is electrophysiology. Now, we're not suggesting for one moment that that's carried on into the clinic, but that should give us some indication as to effective dose in response within 3 to 6 weeks of irradiation. So that's what we're working on at the moment. And then it's going to be a question of personalizing, as you said.